So let's quickly go over what we did last class. So first of all, we figured out that we want your Vref, that is your bandgap reference, to have the form some VBE or proportional to VBE plus, if you just have VBE, you will have 17.2 VT. That we get from equalizing the, what do we equalize? The temperature coefficients, right? The positive and negative temperature coefficients. VBE has a negative temperature coefficient of minus 1.5 and VT has a positive temperature coefficient of 0.086. So together, you put those two together, you get the ratio factor of 17.2. Okay. Then we also figured out something like this. Okay, works very well. Right? You have two diodes. The difference between the diodes, the op-amp forces X and Y to be equal, X and Y. Because of that, the difference voltage appears across R3. Correct? So the voltage across R3 is proportional to what? It's delta VBE. So it's proportional to VT. And if you take the voltage here, it's nothing, so that current through R3 will be proportional to VT again, and that flows to R2, R3 and the base emitter. So overall what you get here is 1 VBE plus R2 plus R3 times the current. And so we got something like this. Correct? Then what we did is we went back. We had assumed, till then we had assumed that IC does not vary with temperature. We went back, included IC variation with temperature also. All it did was it changed the coefficient. Okay? It doesn't do much. It doesn't do much to your equation at all. Okay? So it gives you your minus 1.5 millivolt per degree per degree Celsius or per Kelvin. It changes it slightly. Okay? Not a big problem. Then we realized that we want to implement this in CMOS, so we don't have NPN transistors, right? So we figured out we'll use the PNP transistor, and we implemented something like this. Okay, all we have done is make a diode. That's all it is. Okay. Then we looked at what happens if you have offset in the op amp. Turns out the offset gets amplified by this 1 plus R2 by R3. That's here. Okay. And it also makes your IC1 not equal to IC2. So we figured out there are two ways. One way is to make this R to be a large enough multiple of R2 to be a large enough multiple of R1. That is one way you can take care of things. Second way is to add two series diodes. Right? So these two put together gives you something like this. Putting two diodes together gives you 2 VBE and 2 VT. So it increases that portion relative to VOS. Right? The other thing it does is, just the VT portion unknown, you get an additional factor of M inside the logarithmic argument. Okay? So that's where we stopped. And I think one of you asked me about this connection. Right? Who was it? I don't know. Somebody asked me last time. What about the connection for Q2 and Q4? Okay? So yes, that's a problem. So we need a way to get this to work without making that connection. These two connections. Okay? How do you do it? Any idea? Emitter to base. Absolutely. Okay. Something like this? That will work. That will actually, yeah, that's what we are getting to. Right? This will work very well. What is the problem? The problem is that collector is always grounded. Correct? Collector is always grounded. You can do other things with the base and the emitter. So if you do this, it will take care of the problem. But what else does it introduce? No, 2 VB is what we want. Why won't it be 2 VB? You need to bias it. Right now this I'll call this QA and QB. QA right now the way it is, it's biased only at the by the base current of QB. We don't want that, first of all. What else? What characteristic do you want from VBE of the transistor? We wanted a specific kind of characteristic from VBE. First of all, what did we assume here? Let's go back to this. We started off with this. We had IC1 equals IC2. VB1 equal to IC2 R3 plus VBE2. What did we have here? We said it's 2 VBE and equal to 2 VB, let's say 1, that is VB1 plus VB2 equal to, or VEB, right? VEB1 plus VEB2 equal to IC2 R3 plus VBE3 plus VEB4. So what do you need here? Both transistors have to have the same current, right? If you want it to be 2 VEB, first of all. Second thing, those two currents have to be equal, right? Only if you make those two currents equal, you will get a VT ln some constant term, N. You want a VT ln N, right? So here you have A, here you have NA. You make sure these two guys have the same current, so you basically need to add some kind of current source there, right? Both of them need to have the same current, and that current has to have a characteristic of what? What is the characteristic of IC1 and IC2? What was it? It is a PTAT current, right? PTAT stands for proportional to absolute temperature. Okay? Those are called PTAT, PTAT, all in capital. Okay? So now the current through QA and QB also needs to be PTAT if you want to replicate the same thing. Okay, that is one condition. What else? Okay, so let's start drawing this thing, right? I'm just going to make it like this. I'm just going to do this. I'm just going to add a current source through these two transistors. Okay? A PMOS current source in this case. If you do that, you will get exactly 2 VB. I'll call this. Okay? That's what you will get. Correct? What else do you need? Can you complete this one? You need the same thing, a replica of this on the other side, which will have, so if this is AA, you first of all need NA. Okay? What else do you need? Let's go back to our original band gap. What else do we have here? We have 2 VBE. In this case, all we have done is we have replaced the resistors with the current sources. Correct? what else do we have? Yeah, we have replaced the resistances R1 and R2 using current sources to make sure the currents are equal. What else? You need a feedback loop, right, with the op amp to set Vx equals Vy. Correct? So we are going to replace it with something like this. Let me redraw this guy. I'll just call this R1. And M1. Okay, what else? I need to bias this voltage. Sorry. Okay. This is what this particular band gap looks like. This is your output. So if you look at it, functionally it does the same thing. This feedback loop makes sure Vx equals Vy. Correct? If you do Vx equals Vy, what is the voltage across R1? 2 delta VBE. Correct? So this current becomes P tag. And what are you doing? You are doing the same thing as before. You are adding 1 VBE, 2 VBE to that, and then adding some P tag current times some resistance. Sorry? So you have 2 VBE here. You have 2 VBE here. Okay. You see what I'm saying, right? Let me make it explicit like this. Okay? So this one accomplishes exactly the same thing. Okay, so what else? You have to accomplish one more thing. I mentioned this in passing in class with respect to the other structure. Let's go back to the other guy. Has everyone got this figure? We notice that there is some feedback here. There is feedback to both the positive and negative terminals. You have to be very careful about the amount of feedback. The negative feedback should always be larger than the positive feedback. Correct? You have to do the same thing here. Okay? So you have one loop here. You have one loop here. Okay? Okay, what else? Now this current through the resistor, we said it's P tag. That is also another extremely useful circuit. extremely useful current. Just like we talked about the need for a constant current and a voltage which is constant with temperature, which is your band gap, right? Similar to that, quite often there is also a need to have a p-type current. Simple example, you have an amplifier, let's say a common source amplifier, okay? Suppose you plot the gain, or let's say a common source with say a resistor which is insensitive to temperature. Right now assume that the resistance is constant with temperature. If you increase temperature, what do you expect the gain to do? Will it be constant, decrease or increase? Increase. Anybody? Everybody thinks it will increase? Huh? Sorry? Okay. So I take a common source amplifier. Okay. Let's assume that the resistance is constant with temperature. I am plotting the gain of the amplifier as a function of temperature. The input has some bias also. Okay. So it's VB plus VI. Okay. So the transistor has a bias current. Let us say that bias current is constant for now. It will decrease. Why? Huh? No. This VT is not KT by Q. This is the VT of the threshold voltage of the MOSFET, right? That is not KT by Q. Usually this is represented as VT. This is usually a lot of people use a small t. Some people use VTH for the MOSFET, but yeah. Okay. Actually, what is VT as a function of temperature? Will it increase or decrease? Anybody? Yes? Will come down. Mobility decreases. Is that right? Okay. You should first find out these two things. Okay. That is your homework for today. Find out what happens to VT as a function of temperature. Go back to your devices book. Find out what happens to VT as a function of temperature. Find out what happens to mobility as a function of temperature. That what will increase? Current should decrease. So in other words, so what you are saying is, if in this particular case, if VB is constant, current should decrease. Or so what is kept constant? So VB is kept constant here. Current decreases. Okay, why would it decrease? There are many factors, right? The current equation is very easy to write. So first of all, what all factors change? Threshold voltage. What else? Huh? Mobility. Anything else? That's it, actually. Right? The current equation doesn't have too many unknowns. So mobility and VT. So what do you think? First of all, okay, let's take mobility. I think it's a little bit easier because what is going to happen to mobility? Decrease. Why? Because T power minus what we wrote, T power minus 3 by 2. Okay, but why does it physically, can you think of a reason why it would scattering becomes larger, right? So definitely the mobility, it seems like it should decrease, right? Even though the particles have more energy, the energy goes into the random portion of movement rather than the systematic portion which you are interested in. Okay, so mobility will definitely decrease. Find out what happens to VT. We'll meet tomorrow and then we'll see. If let's say if they both move in the same direction, it's easy to say. If they both move in opposite directions, I also want you to try to find out or think about which one would be more dominant. Let us say VT tends to decrease. Okay, as he said. You said that, right? Think about which will be more dominant, whether it's mobility or whether it's VT. Okay? We'll continue in tomorrow's class.